Good evening, all. The session will begin shortly. At the end of each session, feedback link will be shared in the chat box, as well as the live streaming is there in the YouTube channel. Please make sure that all the participants fill the feedback form on time.
Raghu sir, can we start?
Yes, sir. Yes, sir. We can start.
Akshay?
Yes, sir.
You may start.
Good evening to one and all. Welcome to the Day 4 session of Organic Semiconductor Innovations, a faculty development initiative sponsored by AICTE Training and Learning Academy and organized by Central University of Tamil Nadu. Today, we have two plenary lectures. The first lecture will be delivered by Mr. Raghuvamshi S Rao, Chief Executive Operator, Elixir Technologies. Before going into today's lecture, I would like to introduce the speaker. Mr. Raghuvamshi Rao has completed Bachelor of Engineering in Instrumentation Technology. He is the Chief Executive Operator of Elixir Technologies, Bangalore. He has robust skill in strategic planning, new business development, and marketing. As a company, they offer complete solutions for molecular, solar research and fabrication like DSSC, perovskite, and solar fuels. They have a strategic partnership with the Swedish company Dynamo, which is a spin-off of KTH Royal University, Sweden. A very welcome to Organic Semiconductor Innovations, a faculty development initiative. Over to you, sir.
Thank you, madam. At the outset, I would like to thank the Honorable Vice Chancellor of Central University of Tamil Nadu, Professor M. Krishnan, Professor R. Tirumurugan, Registrar Central University, Tamil Nadu, then Professor S. Nagarajan, Project Coordinator, and Professor John Prakash, Co-Coordinator, Department of Chemistry, for having me for this, sharing my thoughts on what we have developed for molecular solar fabrication techniques. I will just share my presentation. I assume you can hear me well and you can see the screen.
Yeah, it's visible.
Yes. I will just go through some of the details now. It's primarily the fabrication solutions for molecular solar and thin films. And my name is Raghuvamshi and I'm from Elixir Technologies. We are based out of Bengaluru. We will have an outline of introduction and our DSCC solutions, what we do for perovskites and different types of coating solutions. And we could have some discussions in the end. As a company, we started off with manufacturing machines for a unique technique for shelf life extensions called modified atmosphere packaging and quality control. We have a very strong division there. We make end-to-end solutions here. And we have a division which takes care of arboricultural studies with strategic tie-ups with companies from Germany and Sweden. We also work on nanocellulose production and R&D with our tie-up with a company called Masuko from Japan. And then for renewable energy and bioprocess, we have our own manufacturing devices, and we also work with a Lund University spin-out of a company called BPC Instruments for testing biogas optimization and biodegradability, etc. As a company, we were registered in the year 2004. We have a very strong presence in the research and industries sector, primarily with manufacturing fabrication facility for thin film coating, dye-sensitized solar cell, etc. Our first project was incidentally with your first day speaker, Dr. Suraj Soman, which was a DST and CSTR joint initiative for indigenization of the process of semi-automatic line for dye-solar project. And then I'm quite happy today that the same set of instrumentation that we developed for them has been used to, to fabricate the world record solar cell. And this particular project was on a high priority implementation category by the PMO's office, and then it was monitored quite well. We have installed our fab facilities with several CSIR institutes, IITs, and IIMs. We've also done some good exports with our strategic channel partner from Sweden, Dynamo. As technology solutions, we offer solutions for thin film, dye-sensitized and perovskite, of course, with the modified atmosphere and arboriculture. This is our facility in Bengaluru. This is the original team which worked for design and development of all these machines, which I will explain in the due process. DST's representation of this particular technology when it was shared with the institute, respective institute, and covered by what are our capabilities. We work on indigenous solutions, machine manufacturing, end-to-end solutions, and work on cost effectiveness. We have a complete set of team for design and development of different types of machines. This was first envisaged in our understanding, which we presented as indigenous solutions for fabrication of DSSE to NIST, where we start with screen printing, annealing, die coating, and every process was understood, and it was translated into a machine technique which could finally fabricate a DSSE semi-automatic lines. This was primarily possible through our understanding when we traveled to Sweden to have a strategic tie-up with Dynamo, primarily a material-based company. They provide different types of materials for molecular solar and solar fuels. We also did a good amount of studies in Japanese universities, University of Tokyo and Toyota Center for Advanced Solar Studies. We visited these places and tried to understand how these machines are working towards developing the fabrication techniques per se. Then we also are exploring our tie-up with other universities and institutes, and also the International Solar Alliance, for which India is the headquarter, and there are about 104 participating member countries in this. We had a good opportunity to interact with the masters of the molecular solar, Professor Gratzel, Professor Anders Hagfeldt. In fact, Professor Hagfeldt visited us a couple of times in India, and we were also in touch with them on a regular basis. Evolution of solar cell technology from silicon to thin films and dye-solar, perovskite, polymer solar, and novel technologies. This is where we structured the instrumentation requirements, focusing on design, good lower cost, sustainability, and higher efficiencies. Of course, higher efficiencies and sustainabilities are completely material dependent, but we listen to the scientists, and then we try to optimize our solutions towards exactly the requirements needed. Dye-sensitized solar cell primarily focuses on three chemistry-based solar technologies, dye and perovskites and solar fuels. Dynamo, with whom we work with. Applications of DSSC, you heard quite a lot now by previous speakers. We have also had chances of getting these things fabricated in our facility before dispatch. So we have tested some of these DSSCs on real applications. Some of the commercially available DSSCs from Japan, from Sweden, from Israel, and now there are companies in US which are focusing on developing DSSCs, especially for indoor applications and powering IoTs. I have a short video here which explains about the applications of DSSC.
The Internet of Things, or IoT, refers to a network of physical devices and applications connected through the Internet. It is estimated that by 2025, many aspects of our lives will be mediated through 75 billion IoT devices, and a majority of these devices will reside indoors. Further improvement of IoT devices requires that they become autonomous, but for this, a local low-maintenance power source is necessary. In the search for such a source, scientists have explored several options, including photovoltaics. Conventional photovoltaics involve the use of sunlight to power devices through solar cells. These outdoor photovoltaic cells use materials like crystalline silicon or gallium arsenide and are suited to harvest light at visible or near infrared wavelengths, where a large part of the sun's light spectrum is found. However, due to the prevalence of IoT devices indoors, the energy source will naturally have to be indoor illumination, where predominantly light in the visible region is present. Materials like amorphous silicon, organic photovoltaics, and dye-sensitized solar cells, or DSCs, are capable of harvesting light in the visible light range. In a recent breakthrough study, scientists from Uppsala University, Technical University of Munich, and Newcastle University applied a strategy of co-sensitizing dyes to create a novel DSC with whole transport material based on copper complexes. They found that this DSC is capable of power generation at an unprecedented conversion efficiency of 34% at 1000 lux indoor illumination, far outperforming gallium arsenide. When a small array of these DSCs with an active area of 16 centimeters squared was used to power machine learning on wireless nodes, less than 1 millijoule energy was required to compute one inference of a pre-trained artificial neural network with high accuracy. Further, the 152 joules of energy required to train and verify an artificial neural network was harvested by a DSC array with a 64 square centimeter area, comparable to the size of a small smartphone screen, in less than 24 hours at 1000 lux illumination. These new DSCs open up novel possibilities for light-driven autonomous devices, which can change the paradigm of energy usage and promote environment-friendly and sustainable energy practices, directly converting indoor light to structured information.
It would be nice to know that we have crossed, now Indian scientists hold the world record of 40%. I understand probably Dr. Suraj would have mentioned this to you. Now for the indoor light, there is a device manufactured, completely fabricated in India, which has crossed about 40% of efficiency. We all started off with about late 1990 with the first chemistry generation of ruthenium dyes and iodide. And then it moved on to organic dye and cobalt as electrolytes, and then organic dye and copper as electrolytes. There are different chemistries today being applied for DSSC to understand the material strength and the photovoltaic nature, let's say. There are different types of components which we could offer for perovskites and vibrant dyes. Most of these things are presently imported from Sweden, or there are some materials which are also locally made, but these are the things that would be required for the DSSC fabrication per se. Perovskite materials, then more than about 20 different types of organic dyes, ruthenium dyes, new dyes, XY1 and XY1B are well understood. Then I can share more information if you mail me on the requirements and other things, the chemistry structures and how it gels with the electrolytes, especially with the copper complexes. Then performance boosting additives and components for iodide and triiodide requests and things like that. We also had a very interesting experience working with toolboxes for understanding or characterizing the dye-sensitized solar cells, which were primarily came from Sweden, which was tailor-made for DSSCs. And one such machine, what are all the different parameters that we measure here, especially with using photo-induced adsorption spectrometry, and IPC, the toolbox. All these things give you complete understanding of the inside chemistry of dye-sensitized. We have installed a couple of units of these across India. Optical analytical diagnostic of semi-transparent DSSC working electrodes with an active area of 1 centimeter for confirmation of dye injects electrons, and then dye regeneration studies, fundamental charge transfer studies, primarily conducted first at EPFL and Uppsala, and then now world over standard labs are applying the IEA to understand the solar cell chemistries well inside the system. There are good references for such studies. Examples of recent publications for PIA, IPC, and toolbox. So these you might have come across these studies quite well in your studies. What do we do, especially for the instrumentation development, is right from the glass processing to coating techniques to heat treatment, electrode encapsulation, dye loading, and robotics. These things would be explained in detail in my further slides. We work on automated glass cutting, laser scribing. When it comes to coating techniques, we work on screen printing, slot die coating, inkjet, and spray pyrolysis. In heat treatment, we have sintering furnaces and flash IR encapsulators. We work on UV curing devices. Then dye loading, we have a completely automated dye loading units. And we also have developed the robotics for silver line dispensing, then the UV dispensing for encapsulation, then the glass hole drilling, and then the electrode pick and place and electrolyte filling systems. These are some of the actual machines which we have developed and installed in research centers in India. Spray pyrolysis units, glove boxes for thermostates, slot die, complete robotic systems for multifunctional robots, skid-mounted DSSC, etc. I will show you some of the videos of these things. We all start with glass and PET. It could be PET and PEN device, CO substrate. Then the TiO2 is coated, then the platinum coating, followed by the glass and a hole. And polymer minute holes are drilled for electrolyte. It could be different types of electrolytes. If it's a polymer, could be a solid state electrolyte also. We have, this is how we try to understand the project and then develop techniques towards meeting the requirements to complete the fabrication. This is the first 3D view of the project. Yes, today various facilities world over. Very simple device, but very useful. And then for large area and small area DSSCs, we have developed a screen printing technique, completely indigenous. Different patterns can be printed here. Logos are printed, several different patterns as per the need for the discussions that we undertake. Is developed completely tailor-made devices. Then we have slot die coaters, which can be done in inert atmosphere as well as in ambient conditions. We work on sintering furnaces of different dimensions. And we tailor it to different temperature settings with ramp and soak involved in that. Die coating machine, automatic die coating machines, where your semiconductor TiO2 coated units could well absorb the die. We also have hole drilling machines on glasses, which we take care precisely without any chipping of glass. And then this is primarily for the electrolyte filling system. Then the silver grid formation robot, which is again tailored and programmed in such a way that the necessary geometry is achieved for us. This is for your contacts that we draw the silver lines and the current collection. The silver lines are doped with the UV sealant for encapsulation of your photon counter electrodes. So we draw the UV sealant across the silver line, and then it is ready to be encapsulated before the electrolyte filling. Then we use a robotic device again to pile up these two glasses so that it is geometrically precisely placed one over the other, and then without any dimensional change there. And then finally, UV irradiated before the electrolyte filling, so that both these electrodes are well encapsulated between each other. Then we fill the electrolyte. We also have devices for polymer encapsulation if it is a flexible device, where we could use pressure and thermal energy to encapsulate polymer cells. And we also have a special furnace with compression force on heating and heat exchange facility, again for to remove binders and additives, centering furnaces for flexible devices. As we all know, transparency plays a very critical role, and the colors that we could work with for DSSC, which is making these devices more aesthetic, and then also for the required application. We also have solar simulators with IV measuring units. These are LED based. This is some of our installations across India. This is our first small area DSSC, which we done on a unique skid-based system. I will show you the video of this unit.
Elixir Technologies presents automation solutions for die solar research. Introducing multi-technique assembly system with proprietary, unique non-vacuum dispensing, automatic die coating, flip technique for glass hole drilling, precise electrode alignment, and automatic UV curing.
We developed a unique dual head robotic device here for working for
Elixir Technologies presents automation solutions.
Yeah, this is also one of the DSSC device fabrication system. This explains the complete process instrumentation wise as to what are all the techniques that are involved in completing the fabrication line. This was DSSC. We also offer perovskites completely tailored based on the requirements and glove box integrated with all the required units inside the glove box like spin coater or programmable hot plate. All these things can be added into the system with also the chemistry required for basic research on perovskite, where somebody wants to take care, start with the perovskite research as such. I would like to throw some light on the spray coating outline also, introduction to the intermittent spray pyrolysis deposition system for thin film formation. Spray pyrolysis process in reaction chamber is primarily understanding the droplets which falls on the substrate, evaporation of the solvents and vaporization. Finally, the process of small particles on the substrate. Higher substrate temperature, it works between 300 to 600 depending upon the solvents that we apply here. It's intermittent because after every spray falls on the substrate, there could be a temperature drop. So we give time for the substrate to gain the required temperature, again to have the complete particles inside the system. It can be worked with metal clusters, different types of fillings can format, metal oxides, tin oxide, titanium dioxide, then different types of metal sulfides, metal per se, copper and platinum. We have worked with platinum precursors, which we got from Japan, and then it was used in our units here. Different types of substrates can be worked with, metal, glass, and ceramics, except polymer because of the temperature issues there. These are all some SEM photos and cross-sectional morphological size after the FTO was coated using spray pyrolysis technique. Some of the devices that we manufactured and it is put to use, floor type of large area SPD apparatus systems. Film is, we also used a robotic device inside to move the spray nozzle across the glass substrate and also formation of the thin film over the glass substrate. And it can be tailored or monitored according to the thickness required, and the sprays and the cone size can be operated. We can use different types of nozzles here, air-based nozzle or ultrasonic nozzles. And most of the devices that we offer are primarily tailor-made, and we have discussions with the team to understand their requirements. This is primarily a DSC operated unit. Yes, sir. This completes the.
Yeah, it's completed, right? I think student participants can interact with the resource person.
Yes. I have all the details shared with this thing, and in case you want to know more details, you could always send a mail to us, and we will share the required details. It's not primarily a sales discussion or something like that. This is primarily to develop techniques indigenously for any of your needs. So if you want to even discuss with us a particular technique, we are more than willing to offer our thoughts on the same.
So normally you make the like a coating device, right?
Yes, yes. Different types of coating devices, starting from screen printing to slot die coating to spray pyrolysis. We have also tried a little bit on inkjet printing, but we have not installed this unit yet. But we have done some research on inkjet printing also.
Mm-hmm. Means like you have anything like a lab on a chip kind of devices so that we can.
We build for both laboratory as well as pilot studies. Since it is still not gone to the manufacturing level, so we offer laboratory scale as well as pilot scale. Study instrumentation required or machinery required to do fabrication at the pilot level. For example, we have a running project where about 40-50 DSSCs have to be fabricated in a day, so we could offer them the required instrumentation in a larger capacity.
Okay.
Yes, sir.
And usually in they are just trying with the different molecules. Can we control the thickness of that layer, like when we coat it?
Definitely, sir. Definitely, these things are optimized well depending upon your need. So if it is a screen printer, then we work on the mesh size of the screens and then optimize the required thickness there. Of course, it will be before annealing and after annealing, we need to do some studies there. When it comes to spray pyrolysis, the number of sprays and the distance between the cone and the substrate, there are a lot of variables that can give you the required optimization for thickness control and the evenness of the coating.
Actually, I'm worrying about the thickness in the sense that, like, what is the minimum I can go? Whether I can go with a nano centimeter dimension, nano meter dimension.
Post coating, there are some applications where it has gone to some hundreds of nanos. But it is more towards optimizations. The technique, I can say yes, we can work on nano thickness of coating.
Okay. And what about the platform? Actually, if I want to coat it on a quartz material, is it possible to do with your facility?
See, quartz material. See, if it is a small area, if you want to apply spin coating or you want to do, we need to take care very with care that there is no impregnation of the system there. In case it can be screen printed, it is fine. Or if you need a slot die based system, because that can also be thought about. It primarily depends upon the kind of coating material that you would like to apply, if it is in a paste format or it is in a slurry format. Techniques of coating are subjective to the type of material that we would like to apply to. For example, if it is metal and we are able to develop precursors, then it can go very well through through spray pyrolysis. We have had the opportunity to work with platinum precursors in a slurry format, and we were handling in nanometer thickness here. Yes, sir.
I've seen this, they are trying to go it in a industrial level. Okay, so they need this advanced facility.
Yes, sir. But yeah, they have a very strategic project, and then we are applying that through a screen printing process because of the requirement of multiple requirements. Yes. Certainly, yes, sir. Certain, yes.
Now, see, if I want to do something which is like a lab, I want to test something. Okay.
Yes, sir.
For testing, I cannot buy this very costly devices, right?
Yes. Yes.
So if I want to just test this, okay, whether my molecule is working or not, or that kind of level.
Yes.
What kind of you are advising to us?
Sir, see, it depends upon the kind of characterization output that you need. For example, see, if you want to test a DSC that is a lab made and with IV characterizations, these are very economical systems today available with a very simple IV circuitry, less than 50,000 rupees. You will be able to characterize it because it is primarily more towards the software that is offered along with the unit. But you can get a lot of details, but if you want to go in depth and try to understand the charge characterizations and
you have
to go through photo-induced absorption spectrometry, and of course most of the labs are equipped with IPC today, so you will be able to get the details there. When it comes to, we are also working towards developing a toolbox for perovskites to understand some of these things. I will share some initial details to you by email as to how we are working. It is still not ready, so I did not present it today. But we are developing an instrumentation technique where we will be able to characterize some of the perovskites, at least in the lab level. Yes, yes, sir.
Okay, actually, a few questions are there. I think what type of materials could be used for spray pyrolysis techniques? That is one question.
Sir, different types of metal slurries, different types of semiconductor. See, for example, titanium dioxide, AICTE, and metal coatings can be offered. As I showed in one of the slides, we can handle many different types of substrates, except for polymers, and then the chemistry also, which can be coated on the substrates. Yes, especially with the metal as well as titanium dioxide and paste, for example, carbon slurries, and all these things can be handled with. It would need a discussion as to how these precursors are made, and based on that, we will have to design the required temperature and the cone distance between the substrate. All these things can be explained through emails to your counterparts and fellow research scholars and the professors attending this. In case they have a need, we can always discuss that in details. Yes.
Okay.
These are all generic devices which can be applied for coating different types. And of course, all these things are made for research, so it is not for a single application. It has to be versatile in its features. So we take care of these things to adapted to different research needs.
Okay, nice, sir. Actually, I think we have some kind of engineering people, so they want to know about your pre-pyrolysis unit.
Certainly.
Yeah, what about the substrate temperature range? Those questions there are.
See, we have worked with temperature from ambient to 700 degrees, with the rampant soak type of, it can be used as a sintering device or an annealing device. And then with our inside robotics, we work with air-based nozzle or an ultrasound-based nozzle to have a very clean cone falling into the substrate. And then we move these nozzles through robotic handles, both in the periphery in a particular geometry and also in the diagonal geometry, or straight and rectangular geometry or diagonal geometry. And all these things are programmed through a interface device, and then you will understand the whole working of the device when you look into the display of the units. So it is well programmed, and it is also, as I told you, these things are tailor-made. So we try to understand different geometry requirements, substrate sizes, from small, say for example, 3 centimeters by 3 centimeters to, or probably a little less than that also, to almost 300 centimeters by 300 centimeters. That is 1 foot by 1 foot glass unit. We have installed these units across the countries. And as I told you, the people could choose between the different types of nozzles, and we can offer them a host of different types of. If they want a regular device, we can offer them that, and if they want a tailor-made device with much more inputs there, so that can also be considered.
Means you are facilitating the company to make device according to our need, right? Thank you. Actually, one more question. I think we have one question. What is the reason for inability of polymers towards spray technique?
Sir, see, polymers, primarily the substrates are flexible and it cannot withstand high temperature. For example, if you want to spray, see, most of these slurries are prepared with solvents which will have a evaporation temperature of almost about 300 plus. So it will not be able to withstand this temperature. So what we manage through, mostly polymers are used in slot die coating or spin coating. We can manage these things there. So spray pyrolysis is not an advisable technique for polymers due to its inability to handle the temperature required. The slurry temperature required from the spray nozzle, as it hits the thing, the solvents have to evaporate. So we need a very high temperature around and on the substrate also. Yes, sir.
Okay, nice. Any other questions from participants, sir?
Good evening, sir.
Yes, sir.
Yes, proceed, sir. Sir.
Yes, sir. Sir, I have a question. Actually, we talked about this dye sensitized solar cell, right?
Yes, sir.
Whether this cell can be used for wearable one, sir? Okay, because
Sir,
nowadays people are doing some research with a wearable thing, right? That is wearable devices. It can be self-powered. Okay, if it is suitable for wearable needs, it definitely is going to be support for self-powered wearable gadgets.
Yes, yes. Some companies in United Kingdom tried a completely flexible dye sensitized solar cell, but the challenge was the efficiency. You actually needed a large area to cover to get a very small voltage and current characteristics there. Flexible is possible, but we need to optimize that for a particular application. When it comes to glass, we have more liberal understanding there, so it can be applied for various devices there. When it comes to flexible, we are limited in both handling our materials as well as the application per se. But sir, it is possible to develop. People have already worked on flexible, that is polymer-based DSSC. We have some samples also with us. I can share more details to you on the same. It is quite simple to work with that. if it is a stable sample, in a small sample, we can design a very special slot die coater on that. Or if you want roll to roll also, all these things can be worked out to coat different materials and then encapsulate also through temperature and pressure between the counter and photo. Yes, sir.
Okay, sir. Thank you. Yeah, because actually many people are doing some research with the thermal suit. Okay, that is depends on the climatic conditions. The suit, it can be so that is used for warm and cool, right? Okay, so that so the so-and-so solar cell, it can be wearable, means definitely. So it supports the gadgets as well as the thermal suit. Okay, that is my okay. Yes. Thank you, sir.
Thank you, sir. Thank you.
Sir, I think we have a question from Dr. Rajkumar. Rajkumar, sir, you may ask.
Good evening, sir. Very nice presentation, sir. So my question is for dye-sensitized solar cell, why inorganic compounds are not used? Especially, what about their efficiency and what are the problem associated with it, sir?
The first generation was predominantly inorganic, sir, and we have very, very interesting results out of since there was a change in the chemistries. Even today, the ruthenium-based dyes and the iodide, triiodide, electrolyte are working very fine, and all these things can be applied into the system. It is the units are not dependent or primarily going to work only for inorganic or organic. You can use different types of chemistries to develop DSSCs here. It started off with ruthenium-based dyes. You might know that N719 dye, which was incidentally developed by an Indian but settled in EPFL.
So because I'm working in ruthenium complex, sir, that's why I'm curious to know about that particular reason behind this, sir.
As it moved, see, when it comes to when it went towards indoor photovoltaics, people were trying copper-based, and also the organic dyes, which were very critically synthesized in the West, especially in Sweden and Switzerland. So they wanted to test that at 100 lux, 200 lux, and 1000 lux and see. So the most of the papers which came somewhere during around 2020 and to 2023, or even now, you can see that the organic dyes and copper. But as far as I understand, people are also planning to go back to ruthenium-based, so to keep the economy in place. We cannot use expensive materials and develop something which is of not good efficiency, which means that it cannot compete with silicon per se. So that being the case, there is also a thought process where is it okay to go back to the inorganic once again and start relating towards synthesizing more materials there, or trying to use more different types of inorganic materials there. Yes, sir.
Okay, thank you very much, sir.
Thank you, sir. Thank you.
I think we have a question from Gauri. Actually, when we go for multi-layer coating, okay,
yes,
is there any possibility of a self-assembly?
Yes, sir.
Yes. And will that affect the film preparation?
Will it affect what, sir? The
film formation.
Film formation. See, every process would need its own annealing process after coating. So if it is completely material dependent, so if you are working on a particular chemistry which would need a low temperature sintering, then it will not affect the coating. But if we see, for example, TaO2, we coat blocking layer and mesoporous layer together, and then it does not affect the structure of coatings there, sir. It's totally dependent on the type of chemistry that we will work with, and then the suitable coating, also the technique. If you are working on spray pyrolysis, we have handled one after the other coating and with its own respective annealing characteristics.
Okay.
Yes, sir.
Actually, one more question from Google. I think I don't know the terminology. Okay, what about the scope of vehicle and binders for small molecules when we use it for screen printed electronic applications?
So, see, what we focus mainly on the complete, the completed paste when it comes to the screen printing. We try to understand a little bit on the viscosity. But if you are applying, see, post the screen printing, your binders and additives we will have to work with our sintering process as such again, and so that your core material is safe on the substrate per se. So this is a combination of techniques. It is not a deterrent to work with screen printing or a slot die when you add different types of binders or additives to your main material, which has to be applied on the substrates.
Okay, nice. Any other questions, sir, from the participants, sir? Any technical questions, sir? Because we have one expert from the industry, so you can ask, sir. Anything related to coating or solar cell? Any other queries, sir? I think no more questions. I think I am very happy that it was a precise presentation, short and precise. I think Akshaya, are you there? Yeah, please proceed. Akshaya? Okay, I think some technical issue. Okay, anyway, means actually on behalf of the department, especially the public chemistry and ATAL organizers, sir, on this workshop, we are very happy to have you, sir, and it was a very informative. I think we are making a lot of molecules and it is going to like a smart material, sir. So when we tried to caught, we had some kind of difficulty and we solved all our issues, sir. Thank you very much, sir. Thank you for your time.
Thank you so much. Thank you so much, everybody.
John?
Yes, sir.
Yeah. So, good evening to all. Actually, we have another 15 minutes time. The speaker has completed well in advance. So the other speaker, he will be joining at 7:15.
Okay.
So we have 17 minutes there. So I think it is better. Now we're all in a virtual mode. It is better to have a kind of an interaction. And again, though we are collecting feedback and all, and as you know, there are since the things are going through online platform, at times things are not in our hand also, right? So when we look into the profile of the faculty members who have registered, there's a total diversity is too much. So we have people from material science, physics, chemistry, then we have engineering sector, from variety of discipline, from computer science, from electrical engineering and all. So what I feel at times it may be very difficult for many of you to follow, because some of the talks are related to chemistry. Some chemistry is there because organic electronics, we can't avoid chemistry. And again, some aspects are with the physics. So these days the research as well as the area is like this. So I felt, I think many of you maybe also, you may be from physics, maybe problem with part of chemistry, and for a chemistry faculty may be difficult with all. For engineering faculty, it may be difficult. So whatever seeing we while applying for ATAL or in the process of selecting the resource persons, we took utmost care, because you know the conditions, 50% of the resource person to be from the industry and remaining from academia, and two people from international speakers, right? Yeah, that's way we have taken. Even we are going to have a speaker from Australia this weekend. So he's basically he's working on flexible organic electronics. And again, now the next speaker, Professor Justin Thomas, he's also working on organic electronics from IIT Roorkee. Likewise, we have selected, but if you have something to talk to us, you can also talk. Some interaction, so that you can introduce yourself, you can say a few words. Actually, the university we are hosting from Central University of Tamil Nadu, it is down south, it is close to Tanjore. It is about 320 kilometers south of Chennai, right? And we have seen we have participants from 23 states, and as per the registration, and people from north to south and east to west. right? We have diversity is also there. And again, yeah, if you want to say something, you can interact. We have another 10 to 15 minutes time we have. Yeah, it's open to the participants. You can share your thing, and you can maybe many of you may be expert in this research domain also, or you want to do something in this research area. You can because people are there to listen to you. Please. Anyone want to say?
Rajkumar sir, you may start, I think.
Hello, sir.
Rajkumar, Dr. Rajkumar, yeah, please.
Yes, sir. So starting from first day onwards, the program is well systematically organized, and every talk is wonderful, and it's related to our particularly semiconductor research. So you are inviting very excellent speaker from the very diversified institute, and their talk is very much useful for our field, sir. It's very good, sir.
Okay, sir. Thank you. So not only feedback, we can share your experience. If at all anybody is working in organic electronics, or right, you can also share your experience.
Especially for engineering field, we are not having that much facilities, sir. It is very useful for know about the advanced research which is ongoing in the outside of our state also, sir.
Thank you, sir.
Sure, sir.
Anyone else want to comment?
Good evening, sir.
Yeah, good evening.
Yes, sir. Please, sir.
Yeah,
Can you please introduce yourself, sir?
Yeah, please. This is Senthil Murugan, Assistant Professor from SRM Valliam Engineering College, Chennai. So I belongs to Electronics and Communication Engineering Department, sir. Okay.
Right.
Actually, most of the people, yes, sir. Most of the people are working in VLSI nowadays. Okay. I hope everybody know about the India, not only India, US also was initiated towards the semiconductor fabrication. Okay. So that so India has introduced there is a plan in Gujarat, right? Dholara and Assam. Okay, so I think then 2026 we are going to get some IC fabrication. Most of the people are working in front end alone. Back end only few people. Okay, so with respect to my perception, there is a vacancies. 25% of vacancies in front end, but 75% of the people are targeting the 25% job. Okay, and back end there is 75% of the job opportunities are there, but only 25% of the people are eligible, that is deserving to grab the position. Okay, so that back end is not that much easy. Okay, which means we should know from the school days to this all 4 years engineering. Okay, because they should know the solid state physics, they should know the chemistry, organic chemistry, inorganic chemistry, in addition mathematical concepts, in addition electronics and communications, everything should know. Then only the peoples may work in back end. I think these sessions are very nice. Okay, but I thought about the solar cells and the semiconductor and the materials, what sort of materials is going to be used, how the materials is going to be efficient with respect to low power and the speed of operations. Okay, so there is a technology involvement and evaluations with respect to gallium arsenide and gallium nitrate. Then some combination of so and so materials, we may get some new versions. Okay, I'm not familiar with that chemistry level, but we used to develop some devices with device level to system level. Okay, there is a hierarchy from device level, that is a transistor level, to system level. But before device, there may be a semiconductor. The semiconductor is made up of some composite materials. That is your part, the chemistry part and the physics part get involved. Okay, so with respect to that part, they may concentrate, means definitely the people may get the jobs in back end too. Okay, there is a huge vacancies in the back end, but only the limited people are getting the positions because of the skill set. Okay, skill set in back end is very, very tough to increase the position. Okay, this is my perception. Okay.
Right, sir. Right.
Okay.
Anybody else want to interact? You can unmute and you can say, Dr. Vittal, are you there? Yeah, yeah. So anyone else want to interact?
I think we can treat this one as attendance.
What?
I think we can treat this response as attendance today.
Okay. Yeah. So actually in Central University of Tamil Nadu, we in my research group, we are working on designing and synthesizing organic molecules for electronic applications. So we have a good facility for synthesizing new organic compounds, characterizing the organic molecules using various spectroscopic tools. And also we have made a platform to fabricate devices. We are working on fabrication of OFFs, organic field effect transistors, and organic resistive memory devices. So it's good, and we made good publications. As also 10 students have been graduated in this research area. They have graduated PhD in this research area. So there's a scope, and again related to this area, there are globally many institutions are working, starting from Stanford University, like big professors like Professor Bo, and many people, they are working on this research area of organic electronics on diversified devices. And even in US, Singapore, people are working on flexible, foldable devices. They are using new organic materials for application towards this. So it's an emerging area of science. And again, if you see the research publications also, right? Whether you take a physics journals like chemistry or organic chemistry or IEEE, in all this platform, there is the scope for publishing the work related to organic electronics. And beyond that, there are dedicated journals like Organic Electronics from Elixir, Organic Semiconductors from Taylor and Francis. And again, there are many journals are there. Even if you think about prime chemistry journals like AngioChem or Journal of Organic Chemistry, JAX. So they are publishing articles related to design synthesis of new molecules for this electronic application. So people are ultimately working on improving the performance of a device, whatever, whether it's a transistor or a memory device. So that kind of research is being going on globally. And again, there are many societies are also there, starting from India, also their Material Research Society. They have a separate division on organic electronics. And again, organic semiconductors is a separate chapter in IEEE. And if you think about global platform, there are many global, there is many societies are there. Even every year they are conducting many conferences under the theme of organic electronics, organic semiconductors, and flexible electronics, like that. So every year, then and there are many conferences, many workshops are going on globally. So that's a kind of an attraction in this field, right? So if at all someone is near to Thiruvarur and also CUTN, you can make a visit and see the facilities, whatever we have and whatever we are doing. So that's the thing I want to say. And now anybody else want to say? We have another 5 minutes. Professor Justin Thomas will be joining at 7:15 because he's on the way to his home. So he will be joining from there. So anybody else to say something, you can introduce and you can say something about your research area also. So that others will also get benefited out of it.
Sure, I have another question. Okay. Yeah, so you said about some students are doing research in the organic field effect transistor, right?
Yeah.
Okay, if anybody is doing the gate all around FIT, sir, so research in the gate all around, that is a field FIT technology, and nano wire based field effect transistors. If anybody is doing a vertical nano wire or gate all around field effect transistors.
Not like that. The kind of research what we are perceiving is we are making new organic molecules, keeping certain certain design strategy, and based on that we are making molecule and making a thin film organic field effect transistors. Right? We are not working mainly not working on architecture or the devices. So we usually work on bottom gate top contact devices. We fabricate devices like that. And our ultimate aim is for a new material, what about the device performance? For example, transistor, dimmability, on-off ratio, threshold voltage, like we used to measure. And also whatever we are proposing, we will try to give mechanism how it is functioning by using experimental methodology as well as computational techniques like to support whatever our results. So that's the way we are doing, right?
Okay, sir. Then you talked about the threshold voltage, right? What about the threshold voltage in your design, sir? That is organic FET threshold
Sir, it depends,
voltage.
sir. We worked on various types of organic molecules. We worked on porphyrins, we worked on quinolines, we worked on different types of triphenylamines. So it depends upon the molecular structure. So
Okay.
we cannot say, yeah, but we have a, we have.
That is, nowadays many people are doing research in low power. Okay, so which means low power means definitely the threshold voltage also is very low, means it is more sufficient for.
Ultimately, our intention is to have a low threshold voltage, high on-off ratio. That's the thing. That's a core objective. Based on that, we are working.
Okay.
Right. So, anybody else want to interact? Maybe one more person. So, thanks to Dr. Senthil Murugan, sir. Anybody else?
Thank you, sir. Thank you.
Welcome. Dr. Vittal, are you there? I think. Anybody else want to interact? John, you have any message for them?
No, actually, one, two things.
Dr. Varadarajan, you want to say something? Thank you. You are saying.
No, it's our thanks. Okay, few things. Actually, we have one examination towards the end. That is the one thing, and it will be MCQ, multiple choice questions. And when you need the exam, whether in the same Saturday or Sunday, because we are sharing these materials in YouTube. You can watch it again if you wish, and you can prepare for the examination, because the AICTE, our ATAL Academy is asking questions also. We have to share the questions, but okay, whatever we are going to conduct. So if you have any suggestions when you need the examinations, or what is the duration, how many questions you need, if you have any such suggestions, you can tell me now. That's the only thing I want to ask. How many questions you need, duration of the examination, when you need, it can be either on Saturday or Sunday. No response, I think.
I think Saturdays is good enough, sir.
Okay, we have a session up to 7. So what time you need, sir?
So after 7.
Okay, so I can just start at 8 to 8:30 or 8 to 9. That
yes, sir. 8 to 9 is, I think, is convenient for everyone.
Okay, so I can actually it will be online mode only, so I can share the link to the examination in the WhatsApp group. Is that fine for everyone?
Yes, sir.
Okay, I think Sandil Murugan sir is okay. Others, I don't know. At least they can raise
I think question types is going to be objective type.
MCQ only.
MCQ only. MCQ alone, or is there any true or false? Like
it will be MCQ mostly. No true or false model.
Okay.
Yeah.
Thank you, sir.
Any other participants want to comment on that one? Question modality, time, or anything? Okay. And second thing, actually, we have updated your attendance for in the ATAL website. Just to go through that one. If we miss any of your attendance, please let us know, so we can update that one also. So please check that one. I think someone is Dr. Naresh is suggesting Sunday will be preferred for the examination. If someone raise a hand. Sir, any queries, anything, or any comments? Yogesh, are you there? Okay. Okay, I think we'll go with the Saturday itself. So 8 to 9, is it fine, sir? Senthil Mervin, sir?
Yes, sir. Yes, sir.
Total how many questions, sir?
That you tell me how many you need. That is the reason I'm asking. How many questions you need, how long you need, when you need. If you say all these options, I'll plan accordingly.
That is based on the marks, whether you are conducting for 50 marks or 30 marks or 100
Actually,
marks.
as per ATAL Academy, we need to score 70%. That's not the condition.
Yes, sir. Yes, sir.
Yeah,
But the question is from all the
Question is,
sessions or else,
yeah,
from
it will
one
be
session?
It will be from all the sessions, sir.
Okay, sir. Okay.
yeah, definitely. But the question is out of, you may fix 30 marks or 50 marks. Okay, it's not more than that, sir.
Okay, so I'll go with the 50 questions and 1 hour time. Is it fine? Or 30 minutes, sir? Anyway,
Hello?
Yes, Naresh, sir. Tell me.
Sir, can you keep it 30 questions and can you make it on Sunday if possible? Sunday will be having some time to watch the videos, and because we are completely from different background as
Okay.
it was.
I also prefer Sunday, but
we need to watch that video sometime because some are very much completely it is involved in chemistry, a deeper level. We are engineering background.
Okay.
We require some time.
Okay.
If you
So,
can make it,
what I will do,
and that too, 30 questions may be enough, sir. If it is 50 questions, it will be very big time number of questions.
okay, I'll go with the 30 questions, so 30 minutes.
Yes,
No, sir. Some excess time should be there, like more than 40 minutes at least.
30 questions, 45 minutes. I think this is comfortable for everyone, sir. The sir said right, because we are from different specialization. Okay, we are not a chemistry person.
Definitely, sir.
Okay, that's why.
It requires
Okay. Most of the persons are engineering background.
15 minutes more. If it is more, it is comfortable to all, sir.
Actually, this is the format which is followed in other ATAL FDPs also. I just done with one ATAL FDP last week.
Okay.
10 minutes they will give my access time of the questions.
Okay, I can go with the 45 minutes. And I'm giving it 15 minutes extra. Don't worry.
Good,
Okay.
sir. That's very good.
Thank
No,
you,
actually,
Sir, whether we can access these videos after this FDP as well, this in YouTube, so that whenever
in that YouTube link, you can access the video, recorded video also.
up to what time it will be available? Like
Till the exam over. Anyway.
after that exam, is it possible to watch these videos? That is what I'm.
Okay, I'll keep it in my folder. You can have it anytime.
Yeah, that is what, sir. Because we some are very much interesting from industries, so we would like to just go the rear. Whenever we got some time, we will be going through that back. We'll get some more information.
It will be available.
In a single listening, we can't get so many points, right? Sometimes we need to.
Yeah, sure, sir. We'll make sure that it is available for you, sir.
Very informative session, sir.
Thank you.
Thank you very much.
Sir, the link is same to all the sessions.
Yes, sir. We are using same link. So you can have it
for watch the videos in YouTube.
Same, sir.
Same. Okay, sir.
If I'm making any changes, I will update in our group. Don't worry.
Thank you, sir. Thank you so much, sir.
Yeah. So Sunday or Saturday, just finalize it so I can accordingly plan it. Sunday or Saturday exam.
Sir, what is the time? Is there a limited time on Sunday? Or can
you tell me the time? I can give the time. Oh, entire day you need any 40.
Yeah, if it is possible, you can keep some entire day because Sunday only will be having some other works also. Personal works will be there. But when they start the exam, they will be completing within 40 minutes. There is no other way, right?
Yeah, yes, sir.
So if it is possible, can you make it a 4 to 5 hours time stretch so that somebody based on the convenience they will attend?
Yes, sir. Definitely, sir. That also I can do. No worries, sir.
Yeah. That if possible, you can do that.
Okay, sure, sir.
Yes, sir. Yes.
Any other comment from anyone? Because some are suggesting that there are some issues with the rain and network access is not there. You are citing that issue, sir. That is the reason we extended the feedback link up to next morning.
Okay, sir.
So, but today I am seeing less participants. Actually, we have heavy rain here, but we all are online from CUTN. I think our next speaker. Good evening, Jason sir.
Good evening, welcome, sir.
Jason sir, your mic is muted.
Okay, yeah.
Yeah. Good evening, sir. Good evening.
Oh,
Good evening, sir. Welcome.
good evening.
Yeah, please.
Welcome.
Thank you so much. Yeah, we are eagerly waiting for you. Yeah. Now, John, it's over to you, or Akshaya who will be introducing. Akshaya, it's over to you now.
Yes, sir. Yes, sir. Welcome all. The next session of Organic Semiconductor Innovations, a Faculty Development Initiative, Day 4, is going to handle by Professor K.R. Justin Thomas. It is my pleasure to introduce a distinguished academic and researcher in the field of organic electronics. He have completed his bachelor's from Madurai Kamaraj University and master's from American College, Madurai. He have received his PhD from Indian Institute of Technology, Kanpur. Following his doctoral studies, he undertook a series of postdoctoral fellowships at Academia Sinica, Taiwan, first from 1997 to 2003, and again from 2004 to 2006, and another postdoc from University of Massachusetts, USA, from 2003 to 2004. In 2006, he joined as assistant professor in IIT Roorkee and currently as a professor in IIT Roorkee. He has awarded with bronze medal by Chemical Research Society of India, Fellow of Royal Society of Chemistry. In 1997, he received DST Young Scientist Award, IIT Madras. Beyond his academic positions, he served as editor in many reputed journals. A warm welcome to Organic Semiconductor Innovations, a faculty development initiative. It's over to you, sir. Thank you, sir.
Yeah, thank you very much for the very nice introduction. So, can I share my presentation now?
Please, sir. Yes, sir.
Okay, are you seeing my presentation?
Yes, sir.
Yeah,
Fine, sir.
so,
No, it's fine.
yeah, it's fine. Okay. Thank you very much. Thank you very much for the invitation to present on the topic organic emitters for efficient organic light emitting diodes in the faculty development program organized by this institute. I'm very glad that I'm able to meet good number of people during in this online platform. And particularly, I would like to thank Nagarajan for arranging and particularly extending the invitation to me. Okay, so in the next 1 hour or so, I'll be talking about organic emitters. It's a kind of a historical perspective, starting from the initial developments and the state of art today. Okay, so I will not be talking too much about our own research. Recently, we have not been involved seriously about the development of organic emitters for LEDs, but we are working on different fields like photocatalysis and other things. Though we have a sustained program on the organic light emitting diode material developments also. Okay, so most of my talk will be on fundamental aspects related to the developments of organic light emitting diodes, and with some research inputs from our own outcome from IIT Roorkee particularly. I am involved in organic light emitting diodes research from 1999, and we had a temporary breakup from this field for 5 years from 2006 to 2012. Then again we started doing research on organic emitters. Okay, so the work on organic materials is of two types generally. So in first instance, the organic materials are used as sensitizers. So that is, they can absorb light and then transfer the energy, light energy, to other molecules which are not capable of absorbing the light. And the materials which are in fact not capable of absorbing light, receiving light from the organic materials, light energy from organic materials, will do the real work. So in such devices or applications, the organic materials are simply serving as sensitizers, are enhancing the vision of certain materials which are not capable of seeing light. Okay, so there are two prominent applications people might have seen. One is solar cells, another is a photocatalytic reactions. And photocatalytic reactions are very much booming these days, which also have a very strong application from organic materials and organic electronic materials or organic emitting materials. Okay, so the organic materials can also be used for different purpose. That is only, for, showing light. Okay, so that is another aspect of the organic materials. So in the organic sensitizers, what normally we do is we shine light on the materials, and then the materials produce electrons, and these electrons are used for applications. That is what is happening in the solar cells as well as in photochemical reactions. So the generated electrons are used for reactions. And when you are looking at the other side of organic materials which can serve as emitters, they can be used as reporting groups in the sensors, or can be used as an emitting materials in organic light emitting diodes. So in this talk today, we will be mainly talking about the role of organic materials as emitters in organic light emitting diodes. So in this application, you will be seeing that you will be injecting electrons into the organic materials, and then the organic materials gets an electrical excitation. From that, when it comes to the ground state, it emits light. So the operation of LED is completely a reverse of what we have seen in a solar cell, where you shine light on the organic materials and then the organic materials produce electrons. Here you inject electrons or apply a potential on an organic material, and this organic material then produces light. So it's a reverse of what we have seen with this sensitizing application of organic materials. Before I proceed further, I would like to remind all the participants that I have number on this slide. If you have any question related to any slide, you can note down the number of the slide, and then you can, specify me when you are asking a question. So this question is related to this slide or something like that. So there is a slide number on the right, bottom of this slide. Okay, so let's proceed further. So if you look at the organic light emitting diode, so the light emitting diode is a very simple diode structure, which is having a kind of a, burger structure in which you have two lobes of a, bread, and then you have some sandwich in between them. So in the similar way, so now what you will have in an organic light emitting diode is an anode and cathode, and then the sandwich here is an organic emitter. And then the anode and cathodes are generally metals, and you cannot do much with those things. Engineering cannot be done. Modifications, chemical modifications cannot be done. So, there is no much room for development of cathode and anode materials. However, organic materials have, gives a huge potential in the sense that the organic materials, organic emitters can be, chemically tuned, and because of the chemical changes that are taking place, functional group variations that you are performing on an organic emitter, it can have different functional properties. So the functional tuning is possible by a chemical modification. So that gives lot of room for the organic chemist to play a major role in the development of organic light emitting diodes. So in this kind of device, the organic emitters play a major role. And then in order for an organic emitter to function effectively in an organic light emitting diode, to give a high efficiency, it has to have certain characteristics. The first one is the capability to transport holes and electrons. And second is that it should be emitting primary colors such as blue, green, and red. And since there is a lot of electrical excitation and everything taking place, there will be a thermal relaxation and everything. So there will be a lot of heating up taking place in the device. So in order to survive such an operational condition, the molecule should be thermally stable. And it should be also able to harvest singlet and triplet excitons. So I will be coming to this point at a later stage, because once you know certain foundations about the organic light emitting diodes, you will be knowing that why you need the organic emitter that you are using here should harvest singlet and triplet excitons. For the time being, you can just take it as a point that organic emitters should be capable of harvesting singlet and triplet excitons. Okay, so you know that most of the organic emitters are fluorescent in nature. That means that they can go to the singlet excited state and then come to the ground state with the fluorescence emission. So then, while from the triplet excitons can be harvested when you are using an organic emitter, it's a big challenge. Okay, so how this challenge can be overcome, or how this challenge can be addressed, is the major point that I'm going to talk about today. Okay, so if you look at an history of organic light emitting diodes, in the beginning, in 1963, electroluminescence was observed in the anthracene crystals. So this is one of the first report of electroluminescence, a phenomenon, physical phenomenon that was observed in an anthracene crystal. Okay, it required a very high voltage charging and everything, and it is not a typical, organic light emitting diode. It's a device simply containing anthracene crystals, and then electrical charging was performed to realize an emission from anthracene molecules. It is only of historical importance. There is no much, information about this device. Okay, however, later in 1987, Vanslyke and Tong reported a multi-layer organic light emitting diode in which they have used different layers for different functions. Okay, and that gave a very good efficiency, closer to 2%. That is the first, light emitting diode which has shown some promising efficiency, 2.22, nearly 2% efficiency. So in this multi-layer organic light emitting diode, they have used a quinylene complex of aluminum tris-quinylene complex, which served as a green emitter, and then they have used naphthalene based cold transporting material. Okay, so as I have told that, in an organic light emitting diode, you will have an anode and cathode, then an emitting material in between. So now we are seeing multiple layers. So instead of having one organic layer that is emitting in nature, now what you are doing is you are using multiple layers. So this is mainly because of the reason that organic materials cannot, in principle, transport holes and electrons equally. That is what is the problem, obviously, people faced in the very beginning stage. So that is overcome by using multiple layers of organic material. So one material will serve as a hole transporter, while the other will serve as an electron transporter. And if one of these layers can emit light, there's no need to use a third emitting layer. And in this device that was demonstrated by Vanslyke and Tong at the time, they have used ALQ3 as the hole transporting, electron transporting emitter. Okay, naphthalamine derivative simply served as a hole transporter. Okay, so that was an breakthrough that happened in 1987. That was the first multi-layer organic light emitting diode having a promising efficiency. Then that came in 1990. It's also very historical importance. In the meantime, there were several organic materials that were demonstrated for application in organic light emitting diodes, but it was not applied yet for a polymer, because polymers, until now, most of the materials were used in LED by vapor deposition. So if you have to go for a practical application, vapor deposition will not help. You need to have a solution processing, because that is what will help you to make in devices and then display devices, particularly in a large scale fashion. So people then looked at polymers, and the first polymer based OLED that was obtained by a solution processing was reported in 1990. It came from a Cambridge University. That was one of the important milestone in the LED history. Okay, that is, so if you look at these two devices, the small molecule organic light emitting diode that was reported in 1987, as well as the polymer based organic light emitting diode reported in 1990, all worked based on fluorescent materials. And you might have studied in physical chemistry that the fluorescent organic emitters normally work in this fashion, that when it is excited, it can go to the singlet excited state, and from the singlet excited state, when it comes to the ground state, it will give rise to an emission of light. And this is called as a fluorescence. And most of the fluorescent organic emitters cannot undergo this intersystem crossing. That is, they can never go to the triplet excited state unless otherwise you have some additional features in the molecule. So this is what is the problem with most of the organic emitters. So number one is that the singlet excited state of the organic emitter is far away from the triplet excited state of the organic emitter. So the gap between the S1 and T1 is generally large. Okay, so that is the first problem. And second is that you have a spin crossover. You have a singlet state to triplet state. So as per the rules that governs the transitions, electronic transitions, delta S have to be 0. Here there is a change in the spin when there is a transition taking place from singlet to triplet state. So that means that the organic emitters cannot easily undergo an intersystem crossing. So you cannot use the triplet state of the organic emitters in the LED emission. That is what is the important problem with the organic emitters. So if you look at an LED, what happens is when the excitons are found, 25% of the excitons are having a singlet configuration, while the 75% of the excitons are having triplet configuration. That is, normally, because the hole and electrons are combining together to produce the excitons, they can combine in 4 different forms. In that one form, that is the, spins up and down is a singlet state, while the others, where they are both up or both down, are, almost, misaligned kind of thing. So in those cases, it's a triplet state. Okay, so you will have 3 triplet states. So that is altogether coming to 75%. So since the fluorescent molecules cannot undergo intersystem crossing, now you can harvest only the singlet excitons when you are using a fluorescent organic emitter. So now that restricts the internal quantum efficiency of the organic light emitting diodes, which employs fluorescent emitters, to 25%. So that is an internal quantum efficiency. Then in an organic light emitting diode, there is another factor called outcoupling. And outcoupling efficiency is theoretically 20%. So that means 1/5 of 25%, that is 5%. So 5% is the maximum external quantum efficiency that can be realized from a fluorescent organic emitters. But 5% efficiency is not good enough for a practical application. So, since organic materials are not capable of undergoing intersystem crossing, then people looked at alternatives. And then one alternative is nothing but the organometallic compounds. So before let me go to the organic metallic compounds, I would like to give examples of fluorescent LED materials. So as I have told in 1987, this was the molecule that was first used in the LED multi-layer structure. Then in 1989, some red emitting materials based on this kind of motifs were reported. And then anthracene-based derivative was reported as a blue emitter in 1990. And we have also published some papers in 2002 onwards on green emitting materials, which are based on carbazole, and they are considered as at that time as a replacement for ALK3. The difference between ALK3 and then the carbazole-based emitters that I'm talking about are that the carbazole-based emitters can serve as a hole transporting emitters, while the ALQ3 can only serve as an electron transporting emitters. Okay, so there are some advantages because of that also. Okay, so that is a new class of material which are hole transporting in nature but emitting also. And then in 2010, there was a anthracene-based molecule which has shown efficiency crossing the theoretical limit of 5%. So that is an interesting breakthrough. So that gave. So what is the reason for that? I will be addressing about this molecule later on, but this is not a normal fluorescent material. That is what is an important aspect about this molecule. This is the crossover material. It's it's called as an p-type fluorescence material, which was first observed in fluorescent pyrene. P-type delayed fluorescent molecules. Okay, so I will come to that one later on, but this is what is the history of fluorescent LED materials. Now, as I have already told that since the fluorescent materials are not capable of harvesting triplet excitons, now people then looked at organometallic molecules, because the organometallic molecules contains heavy metals such as ruthenium, osmium, iridium, platinum, and so on. So they normally undergo a fissile spin orbit coupling, and that facilitates the intersystem crossing. Okay, so that is what is the beauty about this one. So that was invented in 1998. So by using an iridium complex, they have demonstrated a very efficient phosphorescent LED. The efficiency of these materials were more than 8% at that time. So obviously it is crossing the theoretical limit of 5%, which is possible for a fluorescent LED. So that means that in these kind of devices, you are also harvesting the triplet exciton. That is what the point here. Okay, so here, what is happening here is, our physical chemistry clearly teaches us that when there is a heavy metal, so in this case, you have an iridium, and then you can also have ruthenium, platinum, and other metals. When you have a heavy metal, and that heavy metal facilitate intersystem crossing. And in this kind of organometallic compounds, generally the delta EST is slightly higher than 0.1 electron volt. However, because of the spin orbit coupling, they have a very fast intersystem crossing. That is, the spin orbit coupling constant for this organometallic compounds are very high. So when there is an electrical excitation, you harvest singlet and triplet excitons, and these materials are capable of harvesting both the singlet and triplet excitons. And then the triplet excitons will relax to the ground state with a phosphorescence, and singlet excitons will undergo an intersystem crossing and populate the triplet excited state. So you will have only phosphorescence from these materials. Okay, so it can ultimately give rise to 100% efficiency. Okay, that is what is the advantage about these materials. Okay, so we have realized nearly 100% internal quantum efficiency. Now only we have to do an engineering aspects to improve the outcoupling efficiency. So when you can do that one, you can get everything complete. So there is no more research required for LED. That is what people thought in the beginning of 2000. There is no research required for LED. LED is coming to a saturation. Because phosphorescent materials have come, they can give internal quantum efficiency up to 100%. But there came a problem later. Most of these complexes are crystalline in nature. In order to have a very glassy thin film, which is necessary for long-lasting LED, you need an amorphous material. But these kind of inorganic molecules are crystalline in nature, so they don't have amorphous property. That is the first problem. So that means you cannot use this molecule as such in the device. You cannot use 100% of these molecules. You have to use this molecule as a dopant in some matrix, which is amorphous in nature. So these kind of phosphorescent LED devices are made by doping these iridium complexes in polymer matrices. So this increases the cost of the device. It increases the processing time of the device, manufacturing time of the device. Okay, so that is one of the problem. But at the same time, most of these compounds have a long excited state lifetime, prolonged excited state lifetime. So that also leads to a lot of complications. You will have a lot of side reaction taking place. And most of these compounds have a metal to ligand charge transfer. And then you know that this metal to ligand charge transfer is very weak. And because of that, the emission quantum yield of these complexes are also very low. So even though internal efficiency can be reaching to 100%, because of the low quantum efficiency, now you are reducing the efficiency of the device. Okay, the internal quantum efficiency of 100% can be realized only when the fluorescence efficiency is also 100%. But when the fluorescence intensity is decreasing, that is what is happening in most of the metal complexes. And you might be knowing that in ruthenium and osmium complexes, it is less than 1%. And in iridium, it is not that much low. However, you can have around 10% and 20%. So that means that you are still having a challenge with these kind of complexes. And moreover that, most of these metals are rare earth metals and they are very expensive. And since they are also heavy metals, they can be creating problems in the environment because most of these metals are also carcinogenic. So we have found a solution, but that solution is not an ultimate solution. It is leading to a lot of problems. So that means phosphorescent LED is not a final solution. It gives only a lesson to us that if you can somehow facilitate the intersystem crossing, you can harvest triplet excitons also in the device. Okay, so having learned that one, now we can proceed with that one. So these are some of the examples of phosphorescent LED materials. And then you can see that, as I have already told, that this material was showing an efficiency somewhere around 8%, and it's a green emitting one, iridium compounds. And then later, a lot of other properties were introduced in the complex. For example, in this one, whole transporting ability of this complex was enhanced by introducing carbosol, which is known to be a very good whole transporter. And then the external quantum efficiency nearly doubled from 8% to 16%. And later people found that gold and platinum complexes can also be used as phosphorescent materials. Okay, and then copper complex was also reported in 2011 as a phosphorescent material, giving an efficiency as high as 21.3%. Okay, so they can give very good efficiency provided they are used in a polymeric matrix. Okay, and having said that, there are several disadvantages of using organometallic complexes as a phosphorescent LED material. People then again focus their attention in the early 2010s, that is 2011 and 12, people again focused as organic emitters. Is there a way to make the organic emitter harvest triplet excitons? Okay, there came a new invention called TADF emitters, thermally assisted delayed fluorescence emitter. This is not the only class of compound which are capable of harvesting triplet excitons. There came the P-type fluorescence, delayed fluorescence, and E-type delayed fluorescence, and then the HLCT. These are the three solutions people found around these years. But TADF emitters are more promising in the sense that they can give a very high quantum efficiency. Okay, I will go to this one by one. I will be discussing about everything. The three solutions that I am going to talk about for harvesting the triplet excitons. One is a triplet fusion delayed fluorescence that is called as a P-type delayed fluorescence. This is what we have learned in the physical chemistry very long back, but we have forgotten. It was reported in 1960s, early 60s. Okay, it was first observed in Eocene. That is called as an E-type since it was observed in Eocene. And then the triplet fusion delayed fluorescence was first observed in Pyrene, so it is called as a P-type delayed fluorescence. But in the OLED nomenclature, it is called as a triplet fusion delayed fluorescence. And the E-type delayed fluorescence is called as a thermally activated delayed fluorescence. That is what is TADF. And there is a third solution that is called as a hybridized local and charge transfer. Simply, it is called HLCT. Okay, we will see one by one and understand the basic principles involved in all the three solutions which make the organic emitters to harvest triplet excitons in the light emitting diode. Okay, so in the triplet fusion delayed fluorescence, which was first observed in Pyrene, what happens is the molecule, when we will simply talk about the photochemistry. Later we can extrapolate that one into an LED phenomena. So you have a molecule in the ground state and then you shine light and it gets excited, goes to the singlet excited state. And this kind of molecule, the ground and the first singlet excited states are local excited states. So that means that they are pi to pi star transition. They are involving pi to pi star transition. And at the same time, there is an important aspect about these kind of molecules where the triplet energy of this molecule are nearly half of their singlet energy. So that means that two triplet excitons in principle can have an energy higher than the singlet. So that is what is the criteria required for this one. So that means that when triplet excited states collide with one another, that is called as a TT annihilation process. It can relax to a singlet excited state and a singlet ground state. So one is relaxation, another is an up conversion. Okay, so this can be shown in the Jablonski diagram, something like this. So as I have told in this phenomenon, two triplet excited states will be getting converted to one singlet excited state and one singlet ground state. So that means that one of the triplet excited state is lost to the ground state. One is retained in the singlet excited state, converted into the singlet excited state. So that means that out of the two triplet excited state, you will get only one singlet excited state. So the efficiency in these systems will be 25 plus 75 by 2, because out of the two triplet excited state, only one is converted to the singlet excited state. So you have to divide by 2. So overall, internal quantum efficiency that you can realize in the triplet fusion delayed fluorescent materials is 62.5%. Nevertheless, it's good. It's not very good, but it is good because you are able to harvest half of the triplet excitons. And the upconversion of a triplet excited state into a singlet excited state is called as a triplet annihilation process. And since these molecules are all having a pi to pi star transition, they generally show a very high fluorescence quantum here. You might be knowing that anthracene and pyrene are the compounds which are having very high fluorescence quantum here. These are the molecules which normally show the TTA, that is triplet annihilation process, or TFDF. But the challenging problem with this molecule is that most of the molecules are polyaromatic compounds. Their solubility in the solvents, commonly used solvents, are very low. So the processability is also low. Okay, as you will be seeing with the examples, you will understand that they are all having a elongated conjugation, and because of that, they will be having a very poor solubility in most of the solvents. So you can see these are the examples of the compounds which are showing TFDF. Okay, many of them having anthracene, pyrene, or bifluorine structures, or any polyaromatic systems. And because of this thing, they have only a pi to pi star excitation, and their triplet excited state energy levels are nearly half of the singlet excited state energy level. So that is, triplet excited state is nearly half lying when compared to the singlet excited state in these molecules. Okay, so this is only a historically, important stuff, because, there is no much room for the development of these materials further due to the processability issues. And then the second solution is thermally activated delayed fluorescence. In the thermally activated delayed fluorescence, which can also be explained by a Jablonski diagram as I have shown here. So the molecule is getting excited through the singlet excited state. Now here the singlet excited state is charge transfer in nature. So that means that the molecules should have a donor acceptor structure. That is an important aspect. Then only you can have a charge transfer from donor to acceptor. So the donor acceptor structure is an important criteria for realizing TADF. That is the number one criteria. And in certain molecules, it is observed that organic molecules, the singlet excited state is closer to the triplet excited state. Okay, it's an interesting observation. And when it is coming close, when they are having, well-separated HOMO and LUMO. Okay, when you can have a well-separated HOMO and LUMO, we will see that one shortly. Okay, so that means that the HOMO and LUMO are not overlapping. When the HOMO and LUMO are completely overlapping, you will have a pi to pi star transition. When it is not, when it is partially overlapping, you will have a pronounced charge transfer. When they are not overlapping, there is a charge transfer, but you will not be able to realize that one in the absorption. That is what will happen. Okay, in such molecules, it is found that the triplet excited states are closer to the singlet excited state, and the delta EST, that is the energy difference between the singlet and triplet excited states, are less than 0.1 electron volt. And since the energy is very small, energy separation is very small, this energy gap can be overcome by a thermal energy. That is the reason it is called thermally activated or thermally assisted delayed fluorescence. So now what will happen in this system is that when you are exciting a molecule, organic molecule, by shining light, goes to the singlet excited state, and since the triplet excited state is closer here, by thermal vibrational energy means it will be getting converted to a triplet excited state by an intersystem crossing. And again, it can also come back to the singlet excited state by a reverse intersystem crossing. And then finally, the emission will take place from a singlet excited state. So now, when you have a molecule which is capable of undergoing intersystem crossing and reverse intersystem crossing, there can be two kinds of emission. One is called as an prompt fluorescence. The prompt fluorescence is the emission that is coming directly from a singlet excited state. And then the second emission is delayed fluorescence. And delayed fluorescence is due to inter-system crossing followed by reverse inter-system crossing. So that means that the molecule is excited through the S1 state, goes to the triplet excited state, then comes again to the singlet excited state. So it means that it is spending more time now traveling to the triplet excited state. Then it comes to the ground state with the delayed emission from the same state, that is S1 state. So the characteristics of prompt fluorescence and delayed fluorescence will be almost same. They will be having an overlapping profile, but the lifetime for the prompt fluorescence will be very short when compared to the lifetime of the delayed fluorescence. Why? Because the molecule is going by inter-system crossing to the triplet state, it takes some time, and then comes back to the singlet excited state, it takes some time, then it comes to the ground state. So it will be obviously larger than the lifetime of the prompt fluorescence. So one of the characteristics of TADF materials is that they will have two fluorescence lifetimes. One will be in the nanosecond region, that is the typical fluorescence lifetime, and another will be in the microseconds region, which will be typically a phosphorescence lifetime. Okay, so in some cases, if the inter-system crossing is so fast, you will have a very shorter lifetime also, but it will not be in the nanoseconds region. It will be always in the microseconds region. And these kind of molecules generally will have a charge transfer characteristics, both singlet and triplet state. And in order for the fast SOC coupling to take place, the triplet excited state should have some LE characteristics. So that you might have learned that inter-system crossing can be facilitated when there is a spin-orbit coupling. When there will be a spin-orbit coupling, when the orbital natures are slightly different. That is what is happening in the bits of phenol. Because of the N to pi star transition associated with this one, N orbital and pi orbitals are different in nature. So you will have a SOC, very good SOC there. The same way, you can have a very high SOC in this molecule when the nature of the S1 and T1 states are different. But in TADF molecules, generally they are charge transfer in nature. So the SOC will be very small. So that means that ISC, RSC rates will be very small. And because of that, the delayed fluorescence will be also having a larger lifetime. Okay, so that is what is very important for one to remember here about the TADF. Okay, so now let's look at what are the important aspects about the TADF. So the excited state is charge transfer in nature, that's what I have told. And then there will be a small delta ESD, which is arising from the well-separated HOMO and LOMO. And the radiative rate constant for these compounds, because they are all charge transfer in nature, so they are all very low. And because of that, you will have a low fluorescence quantum yield. And since the SOC is less, at any point of time, you will have a large triplet excited state, so which will lead to a triplet annihilation, that is a unwanted wastage of excitons. Okay, so that is the problem with this one, but there are a lot of ways to overcome these problems. Okay, so that is what is the way the TADF emitters are designed. These are the challenges that are addressed in the design of the TADF emitters. So let me give some examples how the TADF emitters are designed. As I have already told that the TADF emitter should have a donor acceptor structure. And there is a linker. That linker should make the donor and acceptor not overlap with one another in its electronic structure. That is what is an important aspect. Then only you can have a well-separated HOMO and LOMO. Now, if you look at the designs, such as which are prominently reported, normally have a donor acceptor structure. If you look at the molecule that I have shown here, there is a cyanobenzene moiety which acts as an acceptor and carbosol which acts as a donor. And in this molecule, there is a huge steric hindrance because of multiple chromophores loaded on the benzene. And because of that, there is a tilting taking place. That tilting makes steric crowding cause tilting makes the HOMO is confined to the donor unit's carbazole, and then the LUMO is confined to the cyanobenzene moiety. And that lead to a small delta EST. That is what is an important aspect about these molecules. And alternatively, what you can also do is you can make a linker which is non-conjugated type. So in such a case, says there is no electronic communication possible between a donor and acceptor. So donor will contribute to the HOMO, and then the acceptor will contribute to the LUMO. So there will be a well-separated HOMO-LUMO. So that is what is being seen in this molecule. So here, the segment that is shown in red is an acceptor unit because it contains 2 cyano units. And then the segment that is shown in blue is the triphenylamine moiety, which can act as a donor. And since there is an sp3 carbon which is separating these two or connecting these two, there won't be any electronic communication. So the HOMO will be mainly localized on this part, and then the LUMO will be on this part. Dicyanobiphényl moiety. That's what one can say. So because of the well-separated HOMO and LUMO, now you will have a small delta EST in this molecule as well. Then, how to de-link the donor and acceptor. There is a very good concept that was known to all of us. That is cross-conjugation. Okay. As I have shown here, if you have a tetra-substituted benzene derivatives in which the donor moieties are para to one another, and then the acceptor moieties are para to one another, but ortho to the donor. So this is what is the cross-conjugated molecule. So now the acceptor unit, one of the acceptor unit will be conjugated with the other acceptor unit effectively because they are having para orientation, but they will have a poor interaction with the donor because it is ortho to the acceptor. Okay, so the conjugation axes are perpendicular to one another, and there is no effective interaction between these two axes. One can call this one as a donor axis, this as an acceptor axis. There is no interaction between the electronic interaction, effective electronic interaction between the donor and acceptor axis. So because of that, again, if you look at this molecule, the HOMO will be mainly localized on this axis, and then the LUMO will be on this acceptor axis. There will be very poor overlap at this phenyl group for the HOMO and LUMO. So because of this aspect, these molecules will also show a small delta EST. Okay, so now these are the 3 classes of molecule. Now let's look at the examples of molecules that are reported in the literature. So you can see that this is the sterically crowded molecule 4ZIPN showing an efficiency of 19.3. And this molecule was reported in 2011, where you have a donor acceptor structure and then of a steric hindrance, one can say here also sterically crowding is there. So that leads to a tilting and then effective separation of the HOMO and LUMO. And this has been also observed in this copper complex. And this is the cross-conjugated molecule. So you have a donor axis and an acceptor axis. This also lead to a TADF emission. And several other compounds are also reported to have TADF. Okay, so let me briefly explain some of the examples. So this is one of the first examples shown to have a TADF emission. So here you have a donor moiety is here, and this is an acceptor moiety. How you can confirm this one? You can do a theoretical calculation and then see the organization of the HOMO and LUMO. So when you do the theoretical calculation, you find that the HOMO is mainly on this donor part. You can see here. And then the LUMO is mainly on the acceptor part. There is a very good separation of HOMO and LUMO. So this is one of the first criteria required. So you have a donor acceptor structure, and then the HOMO and LUMO are well separated. So the delta EST will be very small. And this molecule is having an absorption. There is no charge transfer absorption because HOMO and LUMO are well separated, and having a fluorescence and phosphorescence almost overlapping. That indicates that the delta EST is very small. And finally, it showed an efficiency of 5.3%. Okay, so which is higher than the theoretically permitted one. So this was in 2011. And later, Adachi group, the same group, reported in 12, 12, and another compound. It's an interesting compound as well. So it was also again in 2011. It's a green TADF emitter where they have used triazine again as a donor, and then they have used bicarbazole as a donor. When they have used only one carbazole, they found that is a non-TADF material. That is a simple fluorescent material. But when they are using a bicarbazole, the donor strength is increased and then steric crowding is increased. That lead to a tilting and then well-separated HOMO-LUMO and small delta AST. You can see here, well-separated HOMO and LUMO. And absorption without the charge transfer transition, and then the emission typical of a charge transfer excited state. And if you look at here, as I have already told that the delta EST, if there is a monocarbazole, 0.35, and then the moment you put bicarbazole, the delta EST is becoming very small. As I have already told that it will have 2 lifetimes, which is sensitive to the temperature as well, because it is a thermally assisted bond. Higher temperature improves the TADF characteristics of the molecule. You can see that the second delayed fluorescent component, which is occurring at the longer lifetime, is seen at higher temperatures. So when you see at low temperature, that is 150 Kelvin, that is a red trace here, there is no delayed component. However, when you increase the temperature to room temperature and beyond that one, slightly, you get the delayed fluorescence. So the room temperature is good enough to facilitate the TADF in these kind of molecules. Okay, so this is another classical example of a blue TADF emitter. So there are 2 compounds that I'm showing here. One is having a triphenylamine donor and diphenyl sulfone moiety. So here the sulfone moiety acts as an acceptor and carbazole acts as a donor. And there are 2 different molecules. One is a strong donor based, triphenylamine based. Another is a weak donor, carbazole based. This was reported in 2012 by Adachi group. And here also, what happens is that when you have triphenylamine, which is shown in the top, the LUMO is mainly on this part, and then the HOMO is spread on the diphenylamine unit as well as on the phenyl unit. So there is a significant overlap of HOMO and LUMO in the case of triphenylamine derivative. But when you go for the carbazole derivative, what you see here is LUMO is very similar to the triphenylamine moiety, triphenylamine compound. However, the HOMO is now restricted mainly to the carbazole unit. There is little overlap only between the HOMO and LUMO. So from this, what one could expect is that the carbazole-based compound will be TADF, and then the triphenylamine-based compound will be a normal fluorescent material. That means this should be capable of harvesting triplet excitons in an LED, so it should give a higher efficiency in an LED. Okay, that is what is being found. So you can see here, when you measure the lifetime for compound 1, this is the compound 1. This compound 1 is showing only one type of fluorescence. See, there is no delayed component. However, when you go for this compound, that is compound 3, here you have a very good delayed fluorescence. So that means that this is showing TADF, but this is not. Or even if it is showing, it is a very weak. Okay, and at the same time, you can also see that when it is having oxygen, that is shown here as a blue trace, oxygen is found to quench the triplet excited state. So you can see that the single exponential decay is observed for the molecule in oxygen. So that means that it is completely quenching the delayed fluorescence here. Okay, that is also proof that it is having a TADF. Okay, so now it is also having a charge transfer excited state, which is solvatochromic in nature, which is showing solvatochromism. And you can see a great enhancement in the efficiency. This molecule is having an efficiency well within the limit of fluorescent-based materials, less than 5%, that is 2.9%. And this is showing a 9.9%. This is one of the important outcome at that time. Okay, but later the same group in 2012 reported based on steric hindrance designed several molecules based on benzonitrile, and all these molecules showed reasonably well separated HOMO and LUMO acid is shown here, and that showed also charge transfer. And they found that this molecular emission can be tuned by increasing the number of carbosol in these molecules. That is one of a good advantage about this molecule. Okay, so far I have talked about two solutions. One is TFDF, another is a TADF. There is a third solution for harvesting triplet excitons as well. That is called HLCT, hybridization of local and charge transfer. Okay, so this is not well understood. However, it can be summarized in the form of a Jablonski diagram as I have shown here. So when a molecule is excited to its singlet excited state, which is predominantly a local excited state, it cannot undergo intersystem crossing from the singlet excited state because the triplet excited state, which is also predominantly LE in character, is too far away. That is, the gap between the S1 and T1 is very high. So you cannot have RASC or RASC in these kind of molecules. So this is what is the general characteristic of organic emitters, which are generally having a pi to pi star excited state. However, in certain molecules, there may be lying a very high excited states, such as S2, S3, or T2, which are having charge transfer characteristics and having similar energy. As I have shown in this Jablonski diagram, in some molecules, the S2 state may be charge transfer in nature, and T2 state may be also a charge transfer in nature, and they will have similar energy as I have shown. That is, the energy separation between the S2 and T2 will be zero almost. So that means that they are having overlapping vibrational fine structures. So they can vibrational levels. So that means that they can easily undergo intersystem crossing. There is no need for spin orbit coupling and so on. So there is no need for thermal assistance. There is no need for energy. The conversion between S2 to T2 and T2 to S2 are spontaneous because the energy separation is zero. So in such cases, even the molecule goes from S2 to T2 state, it cannot come to the T1 state because the gap between T2 and T1 are very large. However, the gap between S22 and S1 are very small, so it can have a facile interconversion from S2 to T1. So in this kind of molecule, the triplet excited states can be converted singlet excited state by a hot RASC process. So why it is called as a hot RASC process? Because the RASC is taking place at a hot level, higher energy level. And by a facile conversion, internal conversion, it will come to an S1 state, and then the emission will take place from an S1 state. Since the emission is taking place from a local excited state, that is a pi to pi star state, these molecules show a very high fluorescence quantum wave. The charge transfer state is only facilitating the hot RASC. Other than that, it has no influence in the emission characteristics. Okay, so these kind of molecules generally show very promising efficiency, and however, their external quantum efficiencies are not very great when compared to the TADF materials. The reason for that one is not very clear at this stage because not much research is focused on this one, because the efficient, like similar to TFDF molecules, these HLCT molecules also did not attract much attention because of these reasons. Okay, so some of the examples I can show here, which are reported, in 2016 by Ma and co-workers, and then we have also reported in 2017 based on the similar structures, carbosol-based structure, HLCT. I will just show how this is realized in these molecules. So if you look at the two molecules that I have shown here, both the molecules are having benzothiazole as an acceptor, and one molecule is having triphenylamine as a donor, which is a strong donor, and other one is having a weaker donor, carbazole. And the donor strength difference makes huge difference in the emission characteristics. Here there is a strong charge transfer. Here there is a weak charge transfer. So now what you have here is a balance between charge transfer and local excitation in this molecule. And that manifests in the emission characteristics also. If you look at the fluorescence quantum yield of this molecule, because it is prominently a charge transfer molecule showing a fluorescence quantum yield of 40%. However, this is not prominently a charge transfer molecule, having an enhanced local excitation as well, showing a quantum yield of 75%. And in the LED, it is showing 3.8%. This is showing 6.95%. It's a huge variation, nearly double. And if you look at the absorption and emission characteristics also, you see that the donor strength is clearly affecting the absorption and emission characteristics. The triphenylamine donor, which is a strong donor, leads to a red-shifted absorption and emission. And a strong donor triphenylamine leads to a huge salvatochromic shift of 94 nanometer. However, the carbazole leads to a small salvatochromic shift of 66 nanometer. So that also again shows that the donor strength variation have a huge effect on the emission characteristics. And then the last one is that when you are plotting a Lippert-Mataka plot, where you are plotting the orientation polar stability of the solvent against the Stokes shift, you are normally expected to get a one straight line relationship, but here you are seeing two straight line relationship. That means the molecule is not showing any variation in the Stokes shift in the nonpolar solvent and showing a huge variation in the Stokes shift when the solvent polarity is increased. So that leads to two slopes, two straight line relationship. Small slope in the non-polar solvent region and large slope in the polar solvent region. So that means that the molecule is having a dual characteristics. They behave as a local excited, behave as a non-polar molecule in the non-polar solvent and polar molecule in the polar solvent. That is mainly because in the non-polar solvent, it goes to the local excited state, and in the polar solvent, it goes to the charge transfer state. So that is a huge difference. So the observation of two linear relationships in the Lippert-Mataka plot is suggestive of a HLCT state in these molecules. Okay, and that we have also found in 2017 that if you are using benzothiazole with a methyl group, you have a methyl group, and because of this methyl group, there is a difference in the charge transfer characteristics of this molecule. Okay, so when the methyl group is tilting the donor unit, the charge transfer interaction is reduced. And if you look at all these molecules, you will come to understand that in this case, the methyl group is on the phenyl side, that is a dummy group. And then the triphenylamine donor is having a stronger interaction with this acceptor. So there will be an effective charge transfer. Here, the donor group will be tilted because of the methyl group. So there will be a poor charge transfer here. Here, still you will have a charge transfer because you have two triphenylamine group, only one is tilted. Okay, so this will give, some expectations to us in the absorption and emission characteristics. That is what is realized also. You can see here, as I have told that, the charge transfer will be more pronounced than D2 and D3. You can see here D2 and D3 having a redshifted absorption when compared to D1 and D4. D4 is not having any charge transfer characteristics and D4 is having a charge transfer characteristics. You can see this one very clearly here. And that is also manifested in the emission. So here there is no charge transfer. So it is having a blue shifted emission. And in all the three compounds now in the excited state, you are having a charge transfer. Okay. All the excited states are similar in nature. So that is the very clear indication that these molecules can have dual characteristics. How to confirm this one? You can do it by a solvatochromism. And then when you do the solvatochromic plot, you see that the D2, D3, D4 all having a bilinear relationship. Static nonpolar region and steep slope polar region. Okay, so that led to a drastic effect as well as in this, the efficiency of the LED devices. They are all having, not so great, but, better than the common fluorescent molecules, which show efficiency around 2.1%. Okay, so we have also found that carbazole can also be utilized to design HLCT molecules. We have done a lot of, variations by putting several groups on the carbazoles. And I would like to give a very simple effect of cyano substitution. What we found is that when you are having a cyano substitution on carbazole, which leads to a balance between Le and Ct states. So suppose, for example, if you are looking at this molecular structure, there is a donor and donor in a linear conjugation. So you will have a donor axis here and acceptor axis here. So this acceptor will be interacting with this donor. So there will be a weak charge transfer here and pronounced Le here. So this kind of orientation in this molecule lead to a balance between a charge transfer and Le. Okay, so the molecular synthesis I will skip, and then I will show that, you can expect certain things based on this molecular organization. That is what is seen in this absorption pattern. Okay, this molecule is having a more pronounced Le state. There is a strong Le peak here, red-shifted peak here, and this molecule that is 36 having a very big charge transfer in this one. Okay, so, and then that is what is being seen here also. You can see that the charge transfer peak absorbed in the absorption for D36 is manifested in the emission characteristics also. It is having a distinctively different. However, for these two, you are seeing a pronounced Le state, so you have a blue shifted emission. And you can also see this one in the Lippert-Pataga plot, you are having a bilinear relationship. And more striking aspect about this one is the well-separated HOMO and LUMO here. So then when you look at the LED performance of these molecules, you see this molecule is showing a high efficiency of 6.5%. That is coming from the hybridization of local and excited state. And particularly comparing these two molecules will give more meaningful insights. You can see here there is no cyano group, there is no electron withdrawing group. So that means that there is no charge transfer. That is having a very, weak line in the Lippert-Pataga plot. And when you introduce a cyano group, there is a charge transfer part that is coming now. Okay, because of that, you have a hybridization and then very good efficiency enhancement in this one. Okay, I can skip this one. This is an illustration of the same concept with the carbazole donor now. Okay, so we have some more time, so I can take some more time, around 10 minutes more, to show some more developments in the LED. That is, after TADF, what happened? So TADF was introduced in 2012, and then a lot of work was going on the TADF emitters to resolve certain issues and problems that were seen with the TADF emitters. Then there came one of the important problem with the TADF emitter is its charge transfer excited state. Because of that, it is having a low fluorescence quantum field and broad emission. And in order for a real device, display device application, you need a very narrow emission, which is not possible to be realized from TADF. So you see that every solution have a problem associated with it. And TADF emitters also have a problem associated with it. And in 2015, there came a new invention that is called multi-resonant TADF emitters. So in these kind of molecules, you have a rigid structure and you have a built-in donor acceptor characteristics. And despite all these aspects, these molecules are showing a very narrow emission. That is what is the beauty about these molecules. An example is shown here. You can look at the characteristics of these molecule, you will be able to understand why these molecules, MRTADF molecules, are showing narrow emission. That is mainly because of the small Stokes shift. And it is rigid. Because it is rigid, it will not undergo reorganization during an excitation. And since there is no reorganization, the absorption and emission wavelengths are closer to one another, and which lead to a small Stokes shift. And that leads to a narrow full width half maximum in the emission. So you will have a big one. So you can look at this one and understand this even better. So as I have shown here, you can see that the singlet excited ground state goes to the singlet excited state, which is showing a reorganization. So because of that, there is a very good Stokes shift. And then when the fluorescence is taking place from here, the absorption is taking place from this vibrational state, you have a huge broadness in the emission. That is what will be a typical fluorescent molecule as well as TADF molecule, which is having a donor acceptor structure. But when you go for an MRTADF material, now it's a rigid molecule, something like that. There is no flexibility in the molecule. And then the molecular organization is in such a way that alternate atoms are donor and acceptor. For example, if you look at here, the red atoms are acceptor atoms and then the blue atoms are donor atoms. So that means that the HOMO is predominantly on the blue atoms, that are the donor atoms, and then the LUMO is predominantly on the red atoms, that are the acceptor atoms. And because of this short range charge transfer, atom to atom charge transfer, they lead to a very narrow spectrum. And this emission is dominated by 0 to 0 transitions rather than other transition forms. Okay, so this way, these MRTADF materials are more attractive. It is giving a solution for the problem that we have faced with the TADF emitters, that is the broad emission and a weak emission. So now you have a rigid molecule having a short range charge transfer, and that is not leading to any relaxation. So you have a very good narrow emission with high quantum efficiency. So these are some of the examples of MRTADF emitters. So let me start with this one. You can see very clearly when you look at the HOMO and LUMO, they are all present in the alternate atoms dominantly. And they show very high efficiency as well. And a lot of molecules have been synthesized in this category, having boron as one of the important atom or carbonyl groups as an important atom. So I will be talking about these carbonyl compounds a little bit in more details in the next slides. Okay, so this will give some idea how to convert a normal fluorescent molecule into a TADF molecule and then to an MRTADF molecule. It's an interesting story in my view. Okay, so let me look at, let me give an example based on certain, story. So if you look at the benzophenone based molecules, as I have already told that benzophenone having an N to pi star excitation, so that is vulnerable for a intersystem crossing because of the facile SOCs, spin orbit coupling arising from N to pi star orbital change. Orbital rule is relaxed. Now spin orbit coupling takes place. Spin rule is relaxed that way. Okay, so these kind of benzophenone molecules are generally having a phosphorescence or fluorescence. Okay, and you can have donors on this benzophenone. However, when you are doing a fusion of the benzophenone at this point, okay, with a heteroatom or with a carbon, you can have a different molecules. The molecules will have a structure something like that. It will be, if the X is carbon, then you will have an acridone kind of molecules. And the moment you have a fusion here, you see that these molecules are now TADF in nature. Very good transition of fluorescent or phosphorescent molecule getting converted to a TADF molecule. What is the good property that you are retaining in this molecule is the spin orbit coupling that is taking place in benzophenone. Now, by fusing, you are adding additional dimension to the molecule. Now the molecule becomes a rigid donor, rigid molecule also. Okay, and you can take a system where you have X equal to N phenyl, and then you can have a further fusion. So N phenyl and then have a further fusion. So now what you have done here is an acceptor here and a donor here, and an additional fusion lead to an MR-TDF. That means that alternate atoms are now becoming donor and acceptor, inheriting HOMO and LUMO respectively. Okay, so you can have the X group, anything like oxygen, sulfur, carbon monoxide, carbonyl, CME2, NPH, selenium, SO and SO2. A lot of variations have been found. And let me give examples to illustrate my point, why the benzophenone molecules are either fluorescent or, sometimes even TADF. But, it's not generally, a particular class. So if you look at here, when you have only one carbazole on the benzophenone, it is a room temperature phosphorescent material having a delta EST very high than 0.5 electron volt. When you increase the number of carbazole on the benzophenone, that is the donor loading, you find the delta EST is decreasing from 0.6 to 0.3. That makes the molecule TADF in nature. And alternatively, you can also change the donor, the weak carbazole donor, to a strong acridine donor. Thereby, you can have a drastic reduction in the delta EST to 0.0 almost. And that makes the molecule TADF in nature. So that you can see that by increasing the donor loading also you can do this one. Okay, so this is the case with benzophenone. So for benzophenone molecules, in order to realize TADF, you need to increase the donor loading, or you have to increase the donor strength. That is what the lesson you are having from this one. But when you have a fusion, as I have already told, you are going towards the fused molecules. You can see that the molecule now altogether invariably becomes TADF. Even when you are having one carbazole, here you have a delta EST very close to 0.3% and it is a TADF molecule. And when you increase the number of carbazole, it has a less effect on this system. And at the same time, you oxidize the sulfur here, you reduce the delta EST further. However, the efficiency decreases. And increase the donor strength by replacing the oxygen with nitrogen. You decrease the delta EST and then increase the efficiency. So there are two aspects. So either increase the acceptor strength to reduce the delta EST at the cost of efficiency, or increase the donor strength to reduce the delta EST and increasing the external quantum efficiency. So what we have learned here is by fusing the benzophenone with a heteroatom, you can have now TADF, irrespective of the number of donors or strength of donor. Okay, so that is what we have learned. So now let's look at this molecule, N-phenyl fused molecule, and then do an additional fusion. What happens? As with an additional fusion, we will result in this molecule. So now this becomes an multi-resonant TADF molecule. So in this molecule, this part becomes a multi-resonant core and this becomes a peripheral core. Okay, so now this will also have a lot of implications in the properties. So you can see that the delta EST of these molecules are slightly high. However, they are all MR-TADF in nature and showing very high efficiency in the LED. Okay, and when you look at deeply at these molecules, you can see that the MR acceptor is mainly on the carbonyl and then alternating atoms, and then the MR donor characteristic is mainly on the nitrogen and the alternate atoms, which are denoted here as blue. And then the periphery generally contributes to the donor. So that means that if you are introducing a donor at this group, you will have a long range charge transfer as well as an MR charge transfer, that is a short range charge transfer in these molecules. That is an interesting aspect. Okay, that can be exemplified with systems. You can see here, when you change the X electron rich, you will have long range charge transfer dominating. So if you look at here, when X is equal to oxygen, this is what is oxygen, and this is sulfur. This is selenium and so on. So what you see here is when you increase the electron richness of X, the peripheral part contributes more to the home. That means the short range charge transfer within the MR core is still there, but additionally the peripheral donor also contribute to the charge transfer. That is the long range charge transfer. So that is dominating here. Okay, so this is the fundamental electronic aspect about these molecules. So now what will happen when you increase the donor strength at the periphery? That is what you have seen here. So now you put a donor on the periphery, what will happen? It will increase the long range charge transfer. So that means that it will reduce the delta EST. That is what you are seeing here. When you put a donor group, the delta EST is all decreasing. Okay, so this can also be seen by looking at this molecule. Long range charge transfer increases as the peripheral donor increases, or the donor strength at the peripheral group increases. Okay, so before concluding my lecture for today, I just want to show certain important observations in the last 2 years. Okay, so what we have seen so far is that you have a simple organic emitter that is fluorescent in nature. And then you have an organometallic compound that is a phosphorescent in nature. Then you have a donor acceptor molecule, which is having a well-separated HOMO and LUMO. They are TADF in nature. And then you have a rigid molecule, fused molecules, which are MR-TADF in nature. And in the TADF as well as MR-TADF, in general for TADF characteristics, you need a donor and acceptor, fragments or atoms. Is it possible to have TADF on donor-only molecule? That is what is reported recently in 2022, that this molecule, which is having a fused structure with one heteroatom such as nitrogen, is capable of showing MR characteristics, that is, donor groups, donor in certain atoms and acceptor at certain atoms. Okay, so as I have illustrated here in this molecule. So this is an important outcome in the sense that certain limitations of these molecules can be avoided in this one. That is, charge transfer reduces the fluorescence quantum yield to some extent. That can be reduced in this one because there is no charge transfer characteristic in this molecule. Okay, so this is the recent observation. We need to learn more about this one by doing more experiments. I hope that in the future, more input on this one will come and then will enrich our knowledge on the design of donor-only MR-TADF emitters. Okay, so with this, I would like to conclude in a summary with the historical timeline as complete thing. So we have seen that how a simple fluorescent organic emitter can be converted to a TADF emitter to harvest triplet excitons by introducing a charge transfer characteristics. And then we have also finally seen that a donor-only material, organic material, can also act as an MR-TADF material emitter. Okay, so we don't know much about what is really happening in this molecule, which is having only donor but still acting as an MR-TADF. It's a recent observation. We need to do more experiments to understand and theoretical calculations to understand the electronic characteristics of these molecules. And to summarize, I have shown in this 1 hour and 15 minutes lecture or so, nearly 1.5 hour lecture, how to increase the efficiency of organic light emitting diodes more than 5%. That is the theoretical limit of fluorescence. And how you can design thermally activated delayed fluorescent and hybridized local and charge transfer fluorophores. And then also I have shown that the future of organic emitters in the form of MR-TADF, which is having a donor acceptor structure or all donor structure. Okay, so once again, I would like to thank all of you for listening to me for the last 1.5 hours. And I would like to again thank the organizers for giving me an opportunity to give my lecture on organic emitters in this forum. Thank you all. If you have any questions, you can ask me.
Yeah. Rajalakshmi, you have raised your hand. You can post your question. Hello.
Hello.
Yeah. Thank you, sir. Thank you so much for your wonderful presentation. So, participants, if you have any queries or questions, please raise. You can post in the message chat box, or you can ask browser directly. John?
Yes, sir. Actually, I am waiting for the questions, sir.
Someone raised the hand.
But I think by mistake.
Okay.
Hello, sir. I am having a query.
Yeah, sure. Go ahead, please.
Sir, in slide 20, you have mentioned that a strong donor is needed. If a strong donor is attached, it can enhance locally excited emission and it can weaken the CT. So, like how we have to design a molecule based on that, like whether we have to attach a strong donor or a moderate donor or a weak donor.
See, it all depends on your requirement. I have talked about strong donor and weak donor, particularly for the HLCT molecules. I remember that is for HLCT. Okay, you are talking about this one. Slide 12.
Slide 20. 20.
Yeah, that is for HLCT, of course. So, okay, so in the HLCT molecules, what we have found is that if you are having a weak donor, so here the thing is that you have to balance between charge transfer and local excitation. So that means that you have to reduce the charge transfer. How you can reduce the charge transfer? Only by changing the donor strength or affecting the interaction between the donor and acceptor. So that will reduce the charge transfer, enhance the local excitation. So now you will have a balance between LE and CT. So depending on the acceptor you are using, you may have to use a weak donor or the donor that is tilting from the acceptor, so that you are having a balance between LE and CT. So if you are asking me, we have to go for a strong donor or weak donor, generally I would say weak donor. Weak donor is preferred.
Thank you, sir.
Yeah. Any other questions?
Yeah, good evening, sir.
Yeah, please.
Thanks for your presentation, sir. Yes, sir. Actually, in slide number 3, so you have mentioned about the organic emitters, but it shows only 3 colors, right? RGB.
Yeah.
Okay, so there is a triplet excitation. Is there any possible to develop more than these 3 colors, sir? Okay, nowadays people are doing LEDs with the multicolors, right? By using the one.
Yeah. You see, this is based on. Yeah, I understand your question. This is based on color science. You have the primary colors. These are called, RGB is called as a primary color. By mixing this color at proper proportions, you can arrive at any color.
Okay. So by using tube, right? Tube principles. Okay.
Yeah. So that is why we concentrate mainly on these primary colors. But any color device is welcome. But that will have a limited application. But if you are having a blue, green, and red, you can mix with any other color to make another color.
Okay, so actually, one LED is how many colors can produce, sir? So that is my question. By using one.
But the display devices that you are seeing in the mobile and other things will have a multiple LEDs. Okay. The LED is capable of showing different colors, and then the mixing of the colors by tuning the voltage can be achieved, and then you can generate n number of colors. That is the reason you are seeing all the colors in your screen.
Yes, sir.
Okay, otherwise it is not so possible. Okay, so the simple LED device is different, and then the display device that we are seeing in front of us is very different. That is based on several LEDs.
Okay. Then one more question, sir. Actually, is I came to know you did your PDF in Taiwan, right?
Yeah.
Okay. Yeah. Which means you know very well about the TSMC. Okay. So India initiated some semiconductor manufacturing in Assam and Dodira. What is the future scope with respect to semiconductor in India, sir?
Yeah, we have, see, semiconductor industry will be blooming in the future, obviously. Okay, so we are late, but not very late. That's what I can say. Okay, so we can still do. I see that, if we had started, some 20, 30 years before, we could have now got the market in our hand.
Okay, because
but now we have to fight with the pioneers in the field. That is the problem.
Okay, because most of these students are targeting artificial intelligence and machine learning. Okay, like AIDS. Okay, only few people are turned towards electronics and communications nowadays. That's why my question.
This is understandable because now everyone want the quick money. Okay, without much hard work, people want money.
Okay, sir. Okay, thank you.
Yeah.
Yeah, good evening, sir. Actually, I want to ask one small question.
Yeah, you are welcome.
A small concern, actually. Actually, it is related to TADF. It's like we need a thermal activation to get the delayed fluorescence, right?
Yeah.
So if I record this fluorescence, the normal fluorescence, do I have to go with elevated temperatures? Or
see, the one thing that you have to ensure is that it is under a nitrogen atmosphere, oxygen-free atmosphere. Okay, because the oxygens can quench the triplet excited state.
Yes, sir.
So that is the important thing. But room temperature itself, you will be able to realize TADF because it depends again on the delta EST. That is the energy separation between the singlet and triplet state. If it is very small, you don't need much thermal activation.
Okay.
You need not. Room temperature itself is good enough.
Okay, can we distinguish? Means like I'm just starting with one molecule. I want to check whether it is coming as a delayed fluorescence or normal fluorescence.
Yeah, you can do temperature variation under nitrogen atmosphere on increasing the temperature if the delayed fluorescence is enhanced. That is the lifetime arising from the delayed fluorescence is prominent. It means that you are having. I have shown an example already. You see here.
Okay.
When you increase the temperature, delayed fluorescence is increasing.
Okay. Yeah, fine. So actually, my concern was whether I can see that feature in room temperature, or I have to go to liquid nitrogen temperature to see that.
No. Low temperature is necessary only to know the energy of triplet excited state. Okay. So when you go to the low temperature, you will be able to see the phosphorescence. That time you can measure the triplet energy.
Okay. Fine.
Sir, in most of the cases, why triphenylamine and dibenzo carbazole is used as the donor park, sir? Any specific reason is there?
No, mainly to introduce the steric hindrance. He being a bulky donor. Because I have shown that, for a well-separated HOMO and LUMO, you need, that can be realized by introducing steric hindrance. So people use the sterically demanding groups.
Okay, sir.
Yeah. Thank you so much, sir. Thank you very much for your nice presentation and sparing your valuable time with us. Right, it's a really late night. I think, thank you so much, sir. And
no problem. So,
please make a visit to CUTN whenever you are crossing or coming this side. We are most
surely we can see. I was thinking about this one for a long time.
Definitely we'll invite you. We'll see.
Surely. And then I'm happy to see a lot of enthusiastic people here.
Right.
So they all are from Tamil Nadu or across the
Yes, sir.
country?
Across the country, sir. We are people from 23 states.
Okay, very good, very good,
Yes.
very good.
Yes, sir. So, sir, now it's over to Sweta. Sweta, you can.
Yes, sir. Hope the session came to the end. It's my pleasure to express our sincere thanks to Professor K.R. Justin Thomas. Thank you for your wonderful presentation, sir, and thoughtful responses to all our questions. Thank you, sir. On
Thank you.
behalf of organizing committee, yes, thank you, sir. On behalf of organizing committee, Central University of Tamil Nadu, I would like to express our sincere, heartfelt thanks for both our speakers today, Mr. Raghuvamshi S Rao and Professor K.R. Justin Thomas. Thank you for your wonderful lectures and patiently answering all our questions. I kindly request all the participants to fill the feedback form and join the meeting tomorrow by 6 p.m. Thank you all. Thank you, sir.
Thank you,
sir.
thank
Good night,
you.
sir. Good night, sir.
Good night. Thank you, thank you.
Thank you, sir. Good night, sir.
John, thank you, John.
Thank
Yeah,
you, John.
thanks, sir.
Good night, John.
Good night.
Good night, sir.
Okay, take care. Bye. Bye to all. See you. Bye.